Okay, in this video, we are going to try to do a review of all of Unit 3 of AP Precalculus. It's basically the Trig unit. It's going to be 30 to 35% of the AP exam, and also it's definitely going to be featured in FRQ number 3, and there'll probably be a part about it in FRQ number 4. So let's take a look. First up, we have 3.1, which is just periodic phenomena. So periodic phenomena are just generally things that repeat. And things that repeat most notably for our purposes would be the trig functions, but I've got an example here for you that is not a trig function because I think they could throw this kind of graph at you. They give you this graph and they just say, what is the period of the function? So if that's the case, you just look and see how long it's taking to repeat itself, right? So it's taking 5 units along the x-axis to repeat, so we would just say the period is equal to 5. When I'm doing these sorts of problems, what I typically like to do, because I think it's the most standout feature, is I'll go from maximum to maximum, or I'll go from minimum to minimum, right? Consecutive maximums, how far apart are they? Consecutive minimums, how far apart are they? Another type of thing that will repeat frequently would be things that go in a circle, right? So clocks, an analog clock, for example, will go in a circle, or the hour hand, the minute hand, that kind of thing. Windmills, all kinds of things like that. That's the kind of thing that you might see in an FRQ where they're asking you to like come up with a model for it and that kind of thing. And then the last thing that I want to say about this before we move on is that when you have your function, you can typically write it as f of x is equal to well, actually, you can always do this. F of x equals f of x plus k, where k is equal to the period. And it should really be like k times n, where n is an integer, and you can just keep repeating. Every time you add the period, you get the same value again. All right, that is 3.1. Let's take a look at 3.2. Okay, 3.2 is sine, cosine, and tangent. I'm saying from the unit circle, but actually this is more general. It's from any type of circle. So if we have a circle and we have an angle theta, first we have to know how to describe our angle in standard position. So standard position, vertex is at the origin. You're going to have an initial position, you're going to have a terminal position, and you rotate from initial to terminal position. If you are going counterclockwise, the angle is positive. If you go clockwise, the angle is negative. I think about this so often that to think of what clockwise means, I actually have to think the opposite of counterclockwise, because all you do in math is go counterclockwise. Okay, so we also have an arc, and the arc is what you sweep out as you rotate from the initial position to the terminal position. So we'll have an arc length. You're also going to have a radius for the circle. You can use the arc length and the radius to geometrically calculate the angle in radians, right? And when you do that, we'll say in radians, theta is equal to s, the arc length, divided by r, the radius. So theta equals s over r. You could also say that s is equal to r theta, and then you basically never solve that for r, but you could if you had to. And in general, if you know any two of these things, you can solve for the third thing. It is an equation that you can work with. You might be asked to find something geometrically like that. All right, let's take a look at another thing related to 3.2. I got more for this one. So we also have just a generic circle. And for our generic circle, we're going to have a radius that we'll put in and an angle theta that we rotate. So we're going counterclockwise. That's a positive angle. And we'll label r. So on this circle, where the ordered pair is xy, we can say that sine is y over r. We can say that cosine is x over r. And we can say that tangent is y over x. So r is not going to be 0, but sometimes x might be 0. So sometimes tangent will be undefined. I'll get to that in a second, but in terms of writing it up. The point could be anywhere. It could be in the first quadrant, second quadrant, third quadrant, fourth quadrant. It could be on any of the axes. Doesn't make a difference. Point could just be anywhere. As I mentioned, r is never going to be 0. So sine and cosine are going to exist no matter what you're doing. Whereas tangent will sometimes not exist. Tangent's going to be undefined if x is equal to 0. Now, another thing that I noticed when I was looking at practice tests and just problems put out by College Board, for you to get ready for this thing, they frequently use this terminology. Although you would be able to answer the question without this terminology, I think it's important to realize that this is also true. X is the horizontal displacement from the y-axis, right? So if x is positive, that's how far you are to the right of the y-axis. If x is negative, that's how far you are to the left of the y-axis. And then y is the vertical displacement from the x-axis. So if y is positive, then you're above the x-axis. If y is negative, you are below the x-axis. So it is the displacement. That's a word that will come up sometimes when you're looking at answer choices. But let me tell you, I never saw an answer choice where they gave the correct, like, sine is y over r or cosine is x over r, and then had the incorrect description of the displacements. But you should definitely read them just in case. And then another thing to keep in mind, if r is equal to 1, we actually get the unit circle. And if we get the unit circle, then the ordered pair xy can be thought of as just cosine of theta and sine of theta, right? Because you're doing x over 1 for cosine and you're doing y over 1 for sine. So xy on the unit circle is cosine theta, sine theta. I've always found it very convenient. They're in alphabetical order, so it's not really hard to remember which is which. All right, now we're going to take a look at 3.3. So 3.3 is going to be about sine and cosine values. And my recommendation here is literally just memorize the unit circle. Just memorize it, be able to write it down really fast. I like to have my students do it in under 90 seconds or as close as they can to that. So here's an image of it. I didn't bother to write it. I just went online and found this. I think I got this from Math is Fun. So memorize these values. They are going to be extremely useful. The thing that I always remembered when I was in high school was that sine of pi over 6 is 1/2, which forces the cosine of pi over 6 to be root 3 over 2. And then when you're talking about pi over 3, they just reverse, right? So cosine is 1/2 and sine is root 3 over 2. And then at all the pi over 4s, you just get root 2 over 2s. And you have to decide if they're positive or negative, depending on what quadrant you are in. So memorize that, have it down pat, and it will pay off huge while you're doing anything on the exam related to trigonometry. So in this section, I mean, I probably wouldn't have organized it the way that they did, but they did organize it this way. In a non-unit circle, it's important to remember that cosine is x over r and sine is y over r, and we can solve those for x and y. So cosine of that is x over r, which means that x is r times cosine, and sine is y over r, which means that y is r times sine of theta. So in a general circle, we have the ordered pairs xy are r times cosine and r times sine. Really saves you a little bit of time if you just remember that. It's going to be important later when we talk about polar and complex numbers as well. So x is r cosine, y is r sine, as opposed to the unit circle where x is cosine and y is sine. That's basically all there is in section 3.3. Let's move on to section 3.4. Section 3.4 is about sine and cosine as functions, and so you might see them written in any of these ways. So x is typically the independent variable just in math, right? So f of x is sine of x, f of x is cosine of x, but also in trig, usually you're talking about angles, so you use theta, which is conventionally used for angles. So f of theta is sine of theta, f of theta is cosine of theta. Some things that we need to know. The domain of both of these is all reals. You plug in whatever number you want. You can actually find the sine or the cosine. You might need a calculator. The ranges of both of these naturally, if you don't modify them at all, are both going to be -1 to 1, including -1 and 1. And then both of these naturally have a period of 2 pi, or they repeat every 2 pi. So these are the kind of like the baseline things that we need to remember. Let's take a look at the graph of cosine, right? So we have a cosine graph here. When I look at this graph, I only see 3 things, and like the general shape. I see maximums, intercepts, and minimums. So I would go through and label this as maximum, intercept, maximum. Positive cosine will go max. It starts at a maximum, and from there you don't really have a choice. Maximum, intercept, maximum, and then it'll continue forever. So I always write that pattern down like this. I even think that pattern kind of looks like cosine, so I think it's a little easier to remember. And then we also have sine. So one thing immediately stands out. These graphs look exactly the same. If you didn't pay attention to the x-axis, you wouldn't know which one's which at all. When I look at sine, I also only see 3 things. I see intercept, maximum, and minimum. But sine will always start in an intercept. So it's always going to start in an intercept, and then you're going to go up to a maximum if sine is positive. You're going to go down to a minimum if sine is negative. I should have said the same thing for cosine. Cosine, by naturally, when it's positive, will start at a maximum. If cosine is negative, it will start at a minimum. And again, cosine's a little easier because you don't have a choice of where to go from there. Sine, you start in an intercept. You could either go to a maximum or a minimum. You'll go to a maximum if sine is positive. You'll go to a minimum if sine is negative. So I look at this, I label it up, or I just think about it usually. And this pattern, again, I think the pattern actually kind of looks like the graph. We got intercept, maximum, intercept, minimum, intercept. that sine. Some of my students try to say that or pronounce it. I think it does not sound great when you do that, so I'm not going to try to do that. I have another page about 3.4, but it also might be about 3.5. I'm not really sure. So let's just say this is 3.4.5, like halfway between them. So on this page, I just want to highlight that the things you know about concavity and increasing, decreasing still apply to sine and cosine and literally any function in the universe. So for example, here, these are places where this curve is concave down, and then here is a place, but of course that will repeat, is a place where the curve is concave up. And then increasing, decreasing is probably a little bit easier than concavity. So increasing looks like this, that's where we're increasing, and then decreasing looks like this. And of course, those will repeat over and over again. That's a feature of periodic functions, is that all of their features just keep repeating over and over at some set interval. All right, that's it for 3.4. Let's move on to 3.5. Okay, section 3.5 is going to be about sinusoidal functions. And sinusoidal functions, there's a bunch of things. So first, sine and cosine are just horizontal shifts of each other, which you probably noticed the first time you ever graphed both of them. Specifically in the description of the course, they call out that cosine of x is sine of x plus pi over 2, which means a shift of pi over 2 units to the left. So take sine, shift it pi over 2 units to the left. I'm going to put in a little video here, and you can just watch me take the graph of sine, which is the solid line, and I'm going to shift it pi over 2 units to the left, and it's going to completely overlap the graph of cosine, which is the dotted line, and there you go. All right, so other things that we can do or talk about are the period of the function. So the period is 1 over the frequency. This is terminology that you just need to know. You might be given the period and asked the frequency and asked the period. If period is 1 over frequency, then frequency is also 1 over the period. Another word that you need to know is amplitude. Amplitude is the maximum minus the minimum divided by 2. So that's one way to find it, right? Find the maximum of the graph, the minimum of the graph, subtract them, divide by 2. Another way to find it, and the way that I usually do, is to just find the distance from the midline to the maximum. I haven't really defined midline yet, but this is a review video, so I assume you know. Or we could find the distance from the midline to the minimum. Either of those is going to give you the amplitude of the graph. I'm going to have a picture in a couple of seconds where I put all these on an actual graph. The midline is actually the average of the maximum and the minimum. So max plus min divided by 2. Basically, we've already covered it, but all amplitudes are measured from the midline. I should point out, amplitude is positive, so it's an absolute value. Sometimes you would get negative, like when you're looking at the function, you'll see the thing you think is the amplitude looks negative, take its absolute value. Two other facts that we just need to know. Sine is an odd function. I don't really know how I'm going to animate this, or even I'm not even probably going to bother. That means that if you take the graph of sine and rotate it 180 degrees, so draw a sine on a piece of paper, write top at the top of the paper and bottom at the bottom of the paper, rotate it so the top is now the bottom and the bottom is now the top, you get exactly the same graph. Sine is an odd function. Cosine is an even function, which means if you graph cosine right now and then just fold your graph along the y-axis, just fold the paper in half, the two sides perfectly match up. So it has that kind of symmetry. So cosine is an even function. So now what I'm going to do is I'm going to take a graph and just throw these concepts on it so that we can see it happen, right? So first of all, the period, I usually go maximum to maximum or minimum to minimum. So I'll highlight there is one period, but I could have also done minimum to minimum or that other maximum to the middle maximum. Whatever, there's a lot of ways you can find the period. Another thing would be this is clearly the maximum. This is clearly the minimum. The average of those is the midline. So I kind of eyeballed this. It's definitely at 5. I tried to make it happen. So there's our midline, right? Max plus min divided by 2. Then we'd want to talk about our amplitude, which is from the midline to the maximum or from the midline to the minimum. And I think that's all we want to talk about on this one, which would mean that we are going to move on to 3.6. Okay, 3.6 is going to be about sinusoidal function transformation. So that's going to look like, sort of in general, it's f of x is a sine or cosine, b times the quantity theta plus c. So I'm going to just for a second here point out, I've never really in my life seen this model used with a plus C. Almost always it is minus C. And all of my videos that are like pre-AP Precalc all use minus C because it makes the most sense. But they decided to use plus C. Hopefully they change that in the future, but they have not as of right now. And then finally at the very end, there's a plus D. So let's talk about what each of these do. What I'm going to do is I'm going to like splice in some videos of me just kind of moving things around. So we're going to start with D, which is like the last thing, but kind of makes sense to start with actually. So D is a vertical translation. So you got to pay attention to two different words here. There's going to be translations, which are shifts that do not change the shape. They just change where it is. And then there's going to be dilations, which actually change the shape. So D is a vertical translation. And what D does is it just moves the graph up and down. So I'm probably putting in a video right now, and I'm probably dragging the value of D around, and you can probably see the graph going up and down, and there's like a dotted version of it, and hopefully that all worked out. Okay, so after we talk about that, we then have to talk about horizontal translations, which are C. So C isn't really the horizontal translation. The horizontal translation is actually the opposite of C. Again, translation doesn't change the shape, just changes where it is. And so I'm just going to put a star here and say this goes the wrong way, right? So if C is positive 6, you will shift 6 units to the left. And if C is negative 5, you will shift 5 units to the right, which is a little bit annoying, but it's just the model that they chose. So hopefully I've been showing you a video of what happens while C changes so that you get some sense of what's going on. You can just see it moving left and right, and then that's about it. Doesn't change shape though, just goes left and right. It's a rigid transformation. The next thing that we want to talk about is A. So A is a vertical dilation. So this is actually going to change the shape of the graph. The absolute value of A is actually the amplitude of the graph, right? And remember, that's the distance from the midline to the maximum, the midline to the minimum, or half the distance between the minimum and the maximum. And this is going to change your amplitude by a factor of the absolute value of A. Now, I'm probably splicing in a video right here. You'll notice if A is positive, then the pattern remains the same. So for sine, it's going to be intercept, maximum, intercept, minimum, intercept. For cosine, it's maximum, intercept, minimum, intercept, maximum. When A is negative, it flips the pattern. So all your maximums become minimums, all your minimums become maximums. But A by itself, the absolute value of A, is changing the amplitude. So your maximums go higher, your minimums go lower. That's what A is doing for you. So hopefully I spliced that in. I don't know, I don't really love editing videos, but hopefully I did it. And then finally we have B. B is probably the weirdest one. B is the horizontal dilation. So the word dilation doesn't mean this, but we're going to change the shape of the graph. So we're either squeezing it or we're stretching it out in a horizontal direction. So either things are happening faster or they're happening slower. The distance between maximums will be closer, or rather smaller, I guess, or the distance between maximums will be farther apart. In general, we can say the period is 2 pi divided by the absolute value of B. And because of that, we can say the frequency is the absolute value of B divided by 2 pi. I'm going to put in the video here so that you can see this. Or I don't know, I guess it just looks like an animation or something because you don't know it's a video because it's a video in a video. You can just see as B gets bigger, the period gets smaller. And as B gets smaller, the period gets a lot bigger. And that makes sense, right? Because the period is 2 pi divided by B. So if B is really big, 2 pi divided by a really big number is a small number versus 2 pi divided by a small number, which is going to be a bigger number. Well, where small means less than 1. Okay, so that's all the different transformations that we can do. I kind of highly recommend that you get really good at dealing with these. I have a lot of videos that you can watch separately on this topic, and I definitely recommend that. I'm going to have the name of one in the next section. So let's move on to that section, which will be 3.7. 3.7 is going to be sine. I wrote sine, it's probably sinusoidal. Sinusoidal function context and modeling. So this is a really big deal. So I'm going to have a recommendation here. I really think that you should go do this. You should watch my video called Writing Sine and Cosine Equations from Graphs. It's going to be a link in the description below. There's actually probably a lot of links in the description to videos that I kind of reference or I think you should definitely watch. Maybe I'll put them all in a playlist. Who really knows? Watch this. It's a very popular video. It'll show you exactly how to get equations given graphs, and you're definitely going to have to do that. Now, how do I know that? FRQ number 3 kind of always looks exactly the same, at least as of 2024. It's going to cover sections, or whatever you want to call them, 3.6, 3.7, and then 1.1. And I don't know what 1.1 is because I didn't make a review video for that yet. But what they're going to do is they're going to give you a scenario, and you're going to have to come up with an equation from it. And you're also going to have to like label some points on it. So I'll come back and hit that again. But it's going to kind of look like this. You're given this. There's some scenario that will allow you to like figure out ordered pairs. So I look at this. I'm going to go through my kind of personal process on this. So here's the maximum. Here's the minimum. From that, we can find the midline, which is just going to be 8 plus 2 divided by 2, which is 5. That's the value of D from that model we talked about in 3.6. We also need to find an amplitude. So I'll put it in the midline. The amplitude goes from the midline to the maximum. So that distance right there is 3 units. I usually actually just count it. And then from the midline to the minimum is also 3. I usually look at both of those to make sure that I'm getting the same value. If you don't, then obviously something is wrong. So our amplitude is 3, which means the absolute value of A is 3. We don't know if A is positive or negative until we actually know where to like start this thing. We also need the period. I always go maximum to maximum or minimum to minimum. So we could go minimum to minimum and see that that distance is 6. It's from like 9.5 to 3.5. Or we could go maximum to maximum, which is like 6.5 to 12.5. In both cases, we're getting 6. So our period is 6. Now you got to solve for B. So 2 pi over B is equal to the period. 2 pi over B is equal to 6, which means B is pi over 3. Okay, we're essentially done, but we still don't know where to start. So we just have to make some choices. So I'm going to do 2 examples. Look at this ordered pair. It's definitely 1/2 comma 8. So if I start at 1/2, that means that C is the opposite of that. So C is negative 1/2 in the model that they use. But looking at the graph, I'm starting at a maximum. If you start at a maximum, it's always positive cosine. So positive cosine goes maximum, intercept, minimum, etc. So now we just fill in. We know it's a positive cosine. We know A, therefore will be positive 3, and fill in the rest. If on the other hand, we decide to start at this point, right, at the point 2, 5, so you're going intercept minimum. So if you start at x equals 2, that means C is the opposite of that. So C is negative 2. And if you start at an intercept and go to a minimum, that means you're dealing with negative sign. So it's a negative sign, which means that A is actually negative 3. And you just fill in the blanks, right? So it's not that bad. Definitely watch that other video. I go through a bunch of examples. Makes it really cut and dry for you. I do want to highlight, though, that FRQ number 3, I don't know what just happened here. Oh, there you go. Given data or scenario, make a graph. But actually, that more applies to like the multiple choice. On the multiple choice, sometimes they'll just give you a scenario, they'll describe it, there'll be like a picture, and they'll say which of the following models could model this, I guess. On the FRQ, it's basically always going to look the same. They're going to give you a graph, like an actual graph that just doesn't have an x-axis or a y-axis, and they'll label a bunch of points, and they'll say, like, give the coordinates of these points. That's a thing you'll need to be able to do. And then the next part will almost certainly say, find a possible equation for this. And there's a lot of possible equations. There's an infinite number of them. You just have to get one of them. They might specify it has to be cosine or it has to be sine. I don't know. There's not enough data to be sure of what they're going to do there. But this is what it looks like. 3.6, 3.7, really big deal. I don't know if you can pick up. I keep banging my desk when I say these things. Sometimes the mic picks it up, sometimes it doesn't. Let's take a look at 3.8. 3.8 is going to be all about the tangent function. Let's go back to the circle and see how it relates to that, right? So we have our angle and standard position, meaning the vertex is at the origin. We have the initial position is the positive x, and then you rotate to the terminal position. And then we have theta, and we have the point xy. Tangent is going to be y over x. It's opposite over adjacent, basically, from the triangle, if you visualize a triangle. But in general, it's just y over x. Sometimes it will be undefined because sometimes x will equal 0. I mean, just look at the picture there, right? So another thing, because tangent is opposite over adjacent in this case, which is y over x, which is change in y over change in x to get to that point, we can also say that tangent gives the slope of that terminal ray. So if the terminal side of the angle is a line passing through the origin. The slope of that line will be the tangent of theta. So rise over run, delta y over delta x. That's kind of a big deal. I think it's very fair game for a multiple choice type question. Another place that tangent comes up a lot is converting it to other things, because tangent is y over x, and on the unit circle, y is sine and x is cosine. Tangent is sine over cosine. So you're going to see this a lot. You'll have to replace tangent or tangent squared with sine over cosine or sine squared over cosine squared. Be aware, converting tangents into sines and cosines, definitely a thing. I already mentioned it, but sometimes tangent is undefined. It's going to be undefined anytime cosine is 0, because cosine is in the denominator of tangent. And that just means that x on the unit circle would equal 0. If x is 0, you're just on the y-axis. So anytime an angle is on the y-axis, meaning pi over 2, 3 pi over 2, etc., you're going to get tangent is undefined. And if tangent is undefined, tangent actually has a vertical asymptote. So tangent has a vertical asymptote anywhere cosine is 0. Cosine is 0 when x is 0. If x is 0, you're on the y-axis. So when you hit the y-axis, you get vertical asymptotes for tangent. And that just kind of, you can write it as pi over 2 plus pi times k, where k is an element of the integers. I think it's good to look at a graph of tangent. I do not think they would ask you to graph tangent, but I think they would ask you to be aware of it, because it's specifically mentioned. So if this is our graph of tangent, you can see I put in some vertical asymptotes. In particular, they call out the fact that tangent is concave up and concave down in various places. So I'm just going to highlight the concave down places here. So concave down, and then switches to concave up, which means tangent has a point of inflection at where it intercepts its like fake sinusoidal axis. Tangent doesn't really have a sinusoidal axis because it's not actually a sinusoid, but all those middle points. And then tangent is, the normal tangent graph is always increasing, which means a negative tangent graph would be decreasing. And then the process of graphing this, which again, I don't really think they're going to ask you to do that. There's a process you can use that is really similar to graphing sine or cosine. And again, I would just encourage you to watch a video of it where I'll explain, how to do it in depth. If you're worried about that, I don't really think they're going to ask you to do it, but I would feel bad if I told you it's guaranteed not to be on it without at least encouraging you to be familiar with the process. So that's essentially 3.8. Let's take a look at 3.9. 3.9 is going to be about inverse trig functions. So normally you do the trig, so sine, cosine, tangent, whatever, of an angle, and the answer is a ratio. When you're doing inverse, or what are called arc trig functions, you'll do the arc trig of a ratio, and the answer will be an angle. So the answer, or the thing that an inverse trig function evaluates to, is an angle, and you're going to do inverse trig of a ratio, you're going to get an angle. So notationally, you'll see alternatingly these two things. You'll see sometimes sine with like the inverse notation, so sine inverse, or you'll just see it typed out as arc sine, inverse cosine, arc cosine, inverse tangent, arc tangent. You might see any of those. I've seen both of those on the sample tests, so make sure you're aware of them. It's really important that you know the domains and ranges of these things. And I would actually say the ranges are probably more important than the domains. But honestly, they're all super important. So we have a function, a domain, and its range. So if we have inverse sine, the domain is -1 to 1. The range is negative pi over 2 to pi over 2. You have to memorize that. I'm going to give you a visual way of memorizing it that's based on the unit circle in a second. But negative pi over 2 to pi over 2 is the range. So inverse cosine, same domain, -1 to 1. And the range is entirely different. It's 0 to pi, which is, 0 to pi, which is the top half of the unit circle. And then arctan is kind of like the weirdest one, I guess. So arctan has a domain of all reals, but the range is similar to arcsines, except you do not include negative pi over 2 to pi over 2. So you don't include negative pi over 2 or pi over 2, I should say. The range is actually negative pi over 2 to pi over 2. So you should definitely know where to find these on your calculator, because on the calculator section, you will be asked to evaluate things that involve it, or perhaps like graph a thing, or maybe like use solve, who knows. But just make sure you know where the buttons are on your calculator. TI Inspire, it's very easy to find. It's, the trig button. So here's a way of thinking about these based on the unit circle. Arc sine, so we would say theta is equal to arcsine of y, right? Because sine of theta is equal to y on the unit circle. So if we do the inverse sine of y, the y value, we should get theta. That's going to be from negative pi over 2 to pi over 2 is just the right-hand side of the unit circle. But those angles that are in quadrant 4, which typically you're going to think of as like 5 pi over 3 and 7 pi over 4 and 11 pi over 6, we have to think of their coterminals that are negative. So instead, we're going to think negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6. Commit this to memory, right? So the answer, if you're not using a calculator, the answer to any inverse sine question has to be an angle between negative pi over 2 and pi over 2. It has to be one of the angles you are looking at right now in this part of the unit circle. Inverse cosine, same deal, except the angles aren't weird, right? They just go from 0 to pi, so it's the top of the unit circle. So any angle that's an answer to inverse cosine will come from this part of the unit circle, and you memorize the unit circle. So you can just think about it and pull it off, or maybe at some point you just like wrote down the unit circle and you're just looking at it again, right? It shouldn't take you very long. And then arctan has the same problem as arcsine. We're doing, also I should mention for arc cosine, it was you do the cosine of theta and get x. So think of it as the inverse cosine of x. So if you know the x coordinate, figure out the angle that corresponds to this part of the unit circle. Same for sine, right? If you know the y coordinate, figure out the angle that corresponds to that part of the unit circle, and you'll have your answer. And then arctan, same deal with the angles. Tangent's a little harder because you probably don't have them memorized quite so well, but you should memorize them. So I always think the tangent of pi over 6 is messy. The messy one is root 3 over 3. Tangent of pi over 3 is less messy, so that's just root 3. And then the tangent of pi over 4 is perfect. It's 1. That's the best of them. So you really need to know this. This is going to show up on multiple choice for sure. It also might show up on FRQ number 4, where you have to do some like manipulations with inverse trig, and you'll have to just know values so that you can then work off of them. Make sure you know these values. All right, let's take a look at 3.10, I guess. Section 3.10 is about trig equations and inequalities. I haven't really seen inequalities on the practice exams yet, but like I'm sure they're going to show up at some point on the real thing. I got 3 things you should definitely know right away. 1, know your unit circle. If you have the unit circle memorized, makes it 1,000 times easier. If you don't have the unit circle memorized, you're going to have to like work out a lot of stuff. Not worth it. Just spend like the 5 minutes that it probably takes to memorize the unit circle. Number 2, you should definitely know how to use your calculator, because if this is on calculator, you can either graph to solve, or you can just use the solve function if you have a solve function. Definitely know your calculator. And then the third thing is, if there are inverse trig functions involved, remember the domain and range, and I've drawn these little unit circle figures, right? The domain for arcsine and arccosine is -1 to 1, and then the ranges you can see in these pictures. So arcsine is negative pi over 2 to pi over 2, arccosine is 0 to pi, and then arctan is negative pi over 2 to pi over 2, but not counting negative pi over 2 and pi over 2. So I don't know, like you have to do any number of things when you're doing these. Here's an example problem, I guess. Like maybe solve 2 cosine squared equals negative cosine on 0 to 2 pi, right? So I'm just going to show the work. Move everything to one side. I factor out a cosine. I set each factor equal to 0. And then I just think about the unit circle, like where is cosine 0? It's when x is equal to 0, that's pi over 2 and 3 pi over 2. And then I think, where is cosine -1/2? It's a pi over 3 angle in quadrants 2 and 3. So I just write down 2 pi over 3 and 4 pi over 3. You got to know the unit circle. If you know it really well, it'll go fine for you. If you don't know it well, you're choosing how hard you want the exam to be, right? So make the choice to know the unit circle, which will make everything a lot easier, like everything a lot easier. It's also possible that you might have no solution when you're asked these things. So trig equations are kind of notorious for having no solution. So here's an example that also kind of, I think 3.12 gets mixed in a lot with these, which is just rewriting equivalent expressions. So this problem started out as secant minus tangent equals 0. I changed secant into 1 over cosine, and I changed tangent into sine over cosine. So now I really have 1 minus sine over cosine is 0. So I'm thinking I just need the numerator to be 0, which means I need sine to equal 1. So sine equals 1, actually only at pi over 2, so I don't know why I wrote 3 pi over 2. Maybe I'm gonna cross that out. Ridiculous. Who would think 3 pi over 2 could be an answer? Sine of 3 pi over 2 is -1 because we know our unit circle. It does turn out, though, that the cosine of 3 pi over 2 is 0, so it couldn't have been a solution anyway, but, like, yikes, we shouldn't even have considered it. Get that out of there. Our only possible answer on 0 to 2 pi is actually pi over 2. But at pi over 2, cosine is 0, which means this expression is undefined, so there are no solutions. So it is possible to get no solution. Be on the lookout for that. Really know your unit circle. And just be prepared to do normal algebraic things. Like you might have to factor. It may be quadratic and you have to factor. I haven't seen one of those, but seems, reasonable. And these could certainly be on FRQ number 4 as well. So be on the lookout for that. Let's take a look at the next section. All right, section 3.11 is all about secant, cosecant, and cotangent. These are the reciprocal functions, so they're not inverses, they're reciprocal functions. So secant is 1 over cosine, cosecant is 1 over sine, cotangent is 1 over tangent. I feel like the course really emphasizes these from the standpoint of just being the reciprocals of sine, cosine, and tangent. So in almost every question about any of these, you can really just think like, well, what does cosine do and what impact does that have on secant? Or what is sine doing and what impact does that have on cosecant? Like that kind of thing. In particular, secant will be undefined if cosine is 0 because you can't divide by 0. Similarly, cosecant with sine equals 0 and cotangent with tangent equals 0. But if tangent equals 0, it equals 0 because sine equals 0. So cotan is undefined if tangent or sine are equal to 0. Any of the places where this happens, the graphs of secant, cosecant, and cotangent will have vertical asymptotes, which is something that they do go out of their way to mention. Another thing is sine and cosine have a range of -1 to 1 inclusive. The reciprocal functions have ranges of -infinity to -1 inclusive and 1 to infinity, which is kind of just like everything else. You keep the max and the min, but everything else just switches, right? So sine and cosine are really hemmed in. They have a max and a min. Secant and an amplitude and all that. Secant and cosecant just go wild. They go in the complete opposite direction, right? So if sine is going from -1 to 1, cosecant is going to just take every other value possible. So it's going to go from 1 all the way up to infinity. It's going to go from -infinity all the way to -1. So that's just everything else. Cotangent is 1 over tangent. And tangent is sine over cosine, which means that cotangent is actually also cosine divided by sine. So that's a useful thing to remember, especially because you're going to have to rewrite things in equivalent forms, and they might just give you cotan, and immediately you're like, well, cotan is cosine over sine. On FRQ number 4, they like to ask you to rewrite a trig thing in terms of only like sines and cosines, or only cotan and whatever. So you got to know all these ways of changing one into the other. So secant is 1 over cosine, cosecant is 1 over sine, cotan is 1 over tangent. Cotan is also cosine over sine, like tangent is sine over cosine. There's so many options. But the only other thing that they specifically mention that I think is fair game is tangent. We know is an increasing function. Cotangent is the reciprocal of that. Cotangent is actually a decreasing function. So tangent increasing, cotangent decreasing. I think that's pretty much how you're going to have to handle 3.11 type stuff. Like they really want you to think of it in terms of the reciprocal of the other things. So all of the reciprocals will have trouble. They'll be undefined anywhere the thing they're the reciprocal of is equal to 0. Big deal. Domain, would be anything except where you have a vertical asymptote, ranges as discussed. Let's take a look at 3.12. Okay, 3.12 is going to be about equivalent expressions. Trig is kind of notorious for you can rewrite stuff a million different ways. We just saw that you could rewrite, cosecant, secant, and cotangent in terms of, sine, cosine, and tangent, respectively. So here are some more. Number 1 is probably the most famous of them all, is the Pythagorean identity, sine squared plus cosine squared equals 1. What you can do, though, so memorize that. You have to memorize everything that's on this page. You memorize that. Another form of this, take everything you see there and divide it by cosine squared. You'll get sine squared over cosine squared is tan squared, cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. So tan squared plus 1 is secant squared. And then we could go back to sine squared plus cosine squared equals 1, and we could divide through by sine squared, and we would get 1 plus cotan squared equals cosecant squared. So you should memorize all of those, have them available. You can rearrange them. So you could also say that sine squared is 1 minus cosine squared. You could say that secant squared minus tan squared is equal to 1. These are the equivalent expressions that they're referring to. So you can replace Any sine squared you see with 1 minus cosine squared, etc. You also are required to know the sum and difference formulas for sine and cosine. So I like to write them using this plus minus notation. So sine of alpha plus or minus beta is, so I always say sine of A plus or minus B is sine, cosine, cosine, sine. Sine, cosine, cosine, sine. And it just, you go in order. So it's alpha, beta, alpha, beta. The plus minus is the same. So it's sine of alpha plus or minus beta is sine alpha cosine beta plus or minus cosine alpha sine beta. So read across the top to get sine of A plus B or alpha plus beta. So sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Read across the bottom to get sine of alpha minus beta. We can do the same thing with cosine. So cosine of alpha plus or minus beta. So I always say for cosine, it's cosine, cosine, sine, sine. So I don't even say the alpha and the beta because you don't really need them. And then you just have to remember for sine, the plus minus is the same. For cosine, the plus minus switches. So it's plus minus and then minus plus. So cosine of alpha plus beta is cosine, cosine minus sine, sine. Cosine of alpha minus beta is cosine, cosine plus sine, sine. It just compacts what you have to memorize, but you have to memorize these. We also need to know the double angle formulas. So double angle formulas, what you could do is you could just remember sine of A alpha plus beta and replace every beta that you see with another alpha. So you'd have sine of alpha plus alpha. I think it's better to just memorize it. The sine of 2 alpha is 2 sine alpha cosine alpha. Just memorize it and you'll be able to use it. There's that 2 sitting in front there. Don't forget it. Cosine of 2 alpha, I recommend you know it 3 different ways. So again, you could go to cosine of alpha plus beta and replace every beta with alpha, and you'll have cosine alpha minus sine alpha. That simplifies to cosine of 2 alpha is cosine squared of alpha minus sine squared of alpha. But then what we do is we use equivalent expressions, right? So cosine squared, well, let's start with the first one. Sine squared can be replaced with 1 minus cosine squared. So you have cosine squared minus the quantity 1 minus cosine squared, which gives us 2 cosine squared minus 1. And then you could go back and replace the cosine squared, the original cosine squared, with 1 minus sine squared. So you have 1 minus sine squared minus sine squared, 1 minus 2 sine squared. Just everything on this page, memorize it. You really need to know it. You're taking an AP exam. There's no excuse. Make sure you know these. Make sure that you can rearrange them and recognize them. Here's a couple of examples because, there's nothing to really do here. So I'm not going to walk through them, but just 3 examples of how this might look on the exam. So 1 minus secant squared over tan squared might be just which of the following expressions is equivalent, right? On the domain, assuming it's defined. So you see secant squared, you can replace it with a 1 plus tan squared, and then you just have 1 minus the quantity and blah, blah, blah. You end up with negative tan squared over tan squared. Negative 1 is equivalent to that, assuming that x is a valid value, which the question would stipulate. You might see something like this. 8 sine of x over 2 cosine of x over 2. So immediately I look at that and I'm I see sine of this thing and then cosine of the same thing. It's probably sine of 2 alpha. So I'm just going to put an alpha there. Then remember, sine of 2 alpha is 2 sine alpha cosine alpha. So we'll take that 8 and make it 4 times 2. So 4 times 2 sine cosine, and then that's sine of 2 times, alpha, which just gives us 4 sine of x. So these are the kind of manipulations that you end up doing. They're really important, mathematically, and in terms of AP Precalc, they're going to show up on the exam. Might have something like this. Ignore the 20 for a second. You just see sine, cosine plus cosine sine. In your mind, you're that's sine of alpha plus beta or a plus b. I actually think of them as a and b, not alpha and beta. The plus means you're adding them together, so we add them together. We get this. There's nothing more you can do with it, but it would be choose the multiple choice option or just, write it in terms of a new angle or something. You're going to see this multiple choice. You're going to see this on FRQ number 4. Definitely make sure that you are familiar with all these things. Let's take a look at the next section. All right, 3.13 is going to be all about polar coordinates. Polar coordinates have their own grid. It's based on concentric circles centered at the origin, and then radial lines that essentially kind of model the unit circle angles, but obviously you could get any angle that you want. I've plotted 1 point in the grid. And I'm going to say that this is determined by the coordinates r comma theta. So what is r? R is the distance to the origin, but it's also kind of the directed distance. You can have r be positive or be negative. And then theta is just the normal angle in standard position. So counterclockwise is positive, clockwise is negative. That's all the same as it ever is. Weirdly, you write your ordered pairs as r comma theta. Theta is the independent variable and r is the dependent variable, so that is a switch from x and y. So to convert from polar to rectangular or rectangular to polar, we need to know a couple of formulas. They kind of make sense though. So we have x equals r cosine. That comes from cosine of theta is x over r. And then y is r sine, which again comes from sine is y over r. So x is r cosine, y is r sine. Engrave those in your brain, you're going to use them a lot. R is the distance to the origin, so it's going to be the square root of x squared plus y squared. We need to figure out theta, which is kind of a clever way to do it. It mentions it explicitly in the course description. Theta is the inverse tangent of y over x if x is greater than 0. So if you're on the right-hand side, we're just going to do the inverse tangent of y over x. Remember, if you do the inverse tangent of a negative, you get an angle between negative pi over 2 and 0. You don't get like 11 pi over 6. And then if x is less than 0, meaning you're on the right-hand side of the circle, you're going to do the inverse tangent of y over x, and then just add pi to whatever you get. And this is going to work out for you. It's not really how I typically do this. I prefer to just do inverse tangent of the absolute value of y over x, and then think about what quadrant I want to be in. But this method will always work. And if you're a little shaky with polar, like commit it to memory. There's a lot of stuff you got to memorize, but again, AP course, you signed up for it. Let's convert something. So say we have the rectangular point 3 comma 3 root 3. So there's a lot of 3's there. What you would do is you would go through, you'd calculate r, which is the square root of 3 squared plus a quantity 3 root 3 squared, which is just going to give you 6. Honestly, what I did in my head was I just looked at that and I thought if I divide by 6, I'll get a unit circle point. And because of that, it must mean that r is 6. We have to find the angle. X is greater than 0, so we're just going to do the inverse tangent of y over x. So the inverse tangent of root 3 is pi over 3, right? So you're just thinking like, what angle between negative pi over 2 and pi over 2 has a tangent of positive root 3? And that is pi over 3. You should memorize your tangents. Tangent of pi over 3 is root 3. Tangent of pi over 6 is root 3 over 3. Tangent of pi over 4 is 1. And you can use those to find the inverses. And then we write our ordered pairs, r comma theta, right? So 6 comma pi over 3. Let me introduce a weird idea. Instead of saying it is 6 pi over 3, what we could do is we could rotate to face not pi over 3, but 4 pi over 3. So we're going to rotate pi, right? Just instead of facing pi over 3, add pi to that. Now you're facing 4 pi over 3. Instead of going forward into the third quadrant, go backwards 6 units. This is equivalent to negative 6 comma 4 pi over 3. There are definitely questions on the exam that kind of look like that, or there can be, I should say. No one knows what the actual exam is going to look like, but there could certainly be which of the following is an equivalent expression to this polar coordinate. And then you just look for an angle that differs by pi from the given angle, and you change the sign of r, right? So it's not really that bad. You just got to make those two switches. And then I'll do another one for you. So negative 5, we're going to find r, we're going to find theta. So in this case, because x is negative, you do the inverse tangent of y over x and just add pi to it. So we get 5 pi over 4 in this case. So we could write this as 5 root 2 comma 5 pi over 4. So I could add pi to that angle, or I could subtract pi, right? It doesn't matter if I add or subtract pi, it's just half a circle either way. I'm going to subtract pi to get just pi over 4. If I'm facing pi over 4, but I want to end up in the third quadrant, I need to use a negative r value. So I'm going to say it's negative 5 root 2, and then pi over 4. So let's take a look at the next thing, which actually it's still 3.13. And I have a video that's really related to this. I think you should definitely watch it. I think it can help out a lot in terms of like converting from rectangular to polar and all of that. My recommendation is that you watch the video, Converting Complex Numbers to Polar Form. It's like not that long. It has a bunch of examples and it really goes through everything. Highly recommend that you do that. To convert a complex number into polar form, what we do is we think of a plus bi as just the ordered pair ab. We think of that as a rectangular point, and now this is exactly the same problem as what we were just doing. A would be r cosine, b would be r sine, And then you could rewrite your complex number as r cosine theta plus I times r sine theta. It's really common to factor the r out and to have r times the quantity cosine theta plus I sine theta. So you'll see that a lot. Let me do an example. So we have negative 8 root 3 plus 8I. So, I mean, I look at that and I think if I divided by 16, I would get a unit circle point. So r is definitely 16. Here's the work. X is less than 0, which means that we're going to do the inverse tan of y over x. So that's the inverse tangent of negative 1 over root 3, but I prefer negative root 3 over 3, which is pi over 6, but it's negative, so negative pi over 6. So inverse tangent of negative root 3 over 3 is negative pi over 6, but then we're going to add pi because x is less than 0, so we get 5 pi over 6, and so the angle is 5 pi over 6, r is 16. We can write this as either 16 the quantity cosine 5 pi over 6 plus I sine 5 pi over 6, or 16 cosine 5 pi over 6 plus 16 I sine 5 pi over 6. It's just up to you which one you want to do. I really recommend that you watch a couple extra videos for polar. Polar is like a much bigger idea than AP Precalc just shoves in. But anyway, let's take a look at the next section. All right, section 3.14, 3.14 is polar function graphs. This is like a really straightforward idea, but I don't want to take the time that it would take in this video to really explain it, which I know is lame in a review video. See the description for the links. I have a couple of what I think are great videos of how to just graph a polar function. Doesn't take long to learn. But what I want to highlight here is you're going to base your graph just on the rectangular graph. If you can graph in rectangular, you can graph in polar, for sure. Then the question is, what will this look like on the exam? So what will it look like on the exam? It's not going to be on the FRQs, at least not by the descriptions that they give for the FRQs. So instead, what you're going to have is multiple choice questions. So you're going to be given a function. You have to pick the graph out of a couple of options. You're going to be given the function and part of the graph. So instead of a full cardioid or a full rose curve, it'll probably be a rose curve. Instead of the full rose curve, you have to figure out, so with the part they showed me, what are the values of theta that would generate that? That's an important point. I'm going to show you on the next thing, how I would kind of go about that. And then given a graph, you might have to pick the function, right? So it could go in either direction. In particular, it's not listed anywhere, which is really unfortunate, but I think that you should definitely know rose curves, no cardioids, and no limicons. I have those linked below, right? Those are the links that are in the description. It's going to show you how to graph them, what they kind of generally look like. I think you want a good idea of what those look like so you can just be familiar. But again, this will be multiple choice. So how deep do you want the knowledge to be? I mean, you want to get as close to a perfect score as you can. So, as deep as possible. But I understand you may shirk that a little bit. Rose curves in particular are pretty important. It's a times sine of n theta or a times cosine of n theta. N has to be an integer, which I did not write down, but n will be an integer. If n is even, you get 2n petals, and if n is odd, you get n petals. That's usually enough to decide what function you're looking at. If it comes down to it, another useful thing is that cosine always has a petal on the x-axis. Sine never has a petal on the x-axis. So all you have to do is look at the x-axis, see if there's a petal on it, and if there is, cosine. If there's not, it's sine. Sine sometimes has a petal on the y-axis, but it's not consistent. Cosine, on the other hand, 100% of the time will have a petal on the x-axis. So definitely pause this video or finish this video and then go watch a few of those other videos about how to graph polar. You can get great at that in a very short period of time, especially if you've already mastered graphing rectangular trig functions, which you probably have. So let's take a look at this example. We got r equals 4 sine of 2 theta. And either the question would be, given r equals 4 sine of 2 theta, which of the following is the graph? And then you'll just have 4 graphs and it'll take up a ton of space. Or you might have the graph and it'll just be what is this the graph of? So I provide the graph and the equation. What I would do with 4 sine of 2 theta, my first observation, 2 theta, so n is equal to 2, you get double that because that's even, so you get 4 petals. So I know there are 4 petals. I would look at the answer choices. If one of them had 4 petals, I'd be okay, if 2 of them had 4 petals, I bet one of them would have a petal on the x-axis, and I would know that's cosine. This shouldn't have a pedal on the x-axis, so I would be able to choose, and I'd kind of be done. Another thing they might ask you to do, again, is say like, they'll only show one little part, and they'll say what are the theta values where this happened. So I would take 4 sine of 2 theta, and I would graph it in rectangular, like using knowledge that I possess. I would graph it in rectangular. And then, so I'm going to demonstrate just the relationship here. So this segment of the rectangular graph, theta goes from 0 to pi over 4, r goes from 0 out to 4 in this case, right? So that's this part of the graph. This is the connection that you really want to see. And then the next part, you're going from pi over 4 to pi over 2. So you just kind of like go back from r equals 4 to the origin again as theta rotates. And then you kind of just keep going, right? So now theta is going from pi over 2 to 3 pi over 4, but r is negative. So instead of tracing in quadrant 2, you trace in quadrant 4. If you're in quadrant 1 and r is positive, you go into quadrant 1. So by in, I mean theta. If theta is from quadrant 1 and r is positive, you go to quadrant 1. If theta is from quadrant 1 and r is negative, you go to quadrant 3. And then if you're in 3, you would go to 1. If you're in 2, you go to 4. 4, you go to 2. So like they have this adjacent or vertical, I guess the vertical quadrants are where you end up. Let's kind of like finish this with our picture. So we have this, then we could have this, then just like finish the whole thing, right? So that part. So this is how you would identify like, hey, what values of theta generated which part of the graph? It's because you understand the relationship between the rectangular and the polar. It's like it unlocks so many things. You definitely want to be good at that and understand that. So if you can graph rectangular, you can definitely figure out how to graph in polar. All right, let's take a look at the last section from Unit 3 of AP Precalculus. All right, section 3.15 is rate of change in polar. So there's a couple things that I think are really fair game in here, and then there's one thing that I think is a little weird that maybe they'll ask about, but who knows. So the first one is talking about like, are you getting closer to or farther away from the origin? I think that's like a totally valid and really useful question to ask later in calculus. So let's go over that. Keep in mind, f of theta is r, right? So everywhere you see f of theta, you could just replace it with r. If f of theta, or r, is greater than 0 and f of theta is increasing, then the distance from the origin is increasing. I think that makes a lot of intuitive sense, right? Like if r is 5 and increasing, it's only going to get bigger. You're only going to get farther from the origin. Another way that you can get farther from the origin, or that the distance could increase, is if r is negative and r is decreasing. So if r is negative and decreasing, you are also getting farther from the origin, right? If r is negative 10 and r is decreasing, so then it's negative 11, negative 12, you're definitely getting farther from the origin. So if basically this boils down to increasing, positive increasing, or negative decreasing. They have like a very similar feel, right? Like positive and increasing feel right together, and negative and decreasing. So like if they have the same feel, then the distance is going to be increasing. And then the opposite's true, right? So if r is greater than 0 and r is decreasing, like greater than 0 and decreasing, those have an opposite feel. The distance from the origin is going to be decreasing. So I mean, just think of an example, right? Like r starts at 100, but then r is decreasing. So r is 100, then 99, then 95. You're getting closer to the origin, right? And then you have that fourth scenario where r is going to be negative and increasing. So if r is negative and increasing, you're also going to be getting closer to the origin, so the distance to the origin is decreasing. So if they have the same feel, the distance is increasing. If they have the opposite feel, then the distance is going to be decreasing. For that last one, think about like r is negative 100, and then r is negative 50. That increased from negative 100 to negative 50. And you're definitely getting closer to the origin, which means the distance from the origin is decreasing. I have another way of thinking about this, because when I think of polar, I'm aware that there's a polar grid. I'm aware that you can graph in polar. I always just think in rectangular. So if we have this graph where we have r on the vertical and we have theta on the horizontal, then when r is equal to 0, right, the horizontal axis in this case, that's the origin, right? If you live with r equal to 0 all the time, you just stay at the origin forever. So the horizontal is the origin. What I'm going to do is I'm going to highlight the places where you are getting farther from the origin. The places you are getting farther from the origin are all of these places, right? So where you are positive and increasing, or you are negative and decreasing. The distance from the origin, which is r equals 0, is going to be increasing. And then similarly, I'm going to just highlight the other parts. So at these places where your graph, your rectangular graph, which is how you can answer these questions, your rectangular graph is positive and decreasing, you're obviously getting closer to the origin, or negative and increasing, you're getting closer to the origin, you're getting closer to r equals 0. So that's how I really choose to remember it. Do they have the same feel? When you get to calculus, you'll learn a slightly different way to think about that. But if they have the same feel, right, like positive increasing, negative decreasing, positive increasing, you're clearly getting farther from the origin. So negative decreasing, you'd also be getting farther. They have opposite feels, you're going to be getting closer to the origin. I think that's a totally valid multiple choice type of question. I would expect it. Another idea related to this, so we have the rectangular graph and we have the corresponding polar graph. If you look at pi over 4 for the rectangular graph, we have a maximum. If you look at pi over 4 on the polar graph, you also have a maximum. At 3 pi over 4 on the rectangular, you have a minimum. And at 3 pi over 4, because r is negative, instead of being in the second quadrant, you are in the fourth quadrant. So I've color-coded them. You have an extrema, right? Would you call that a maximum? Would you call it a minimum? We avoid the issue by just calling all of these extreme values or extremums or extrema, depending on how many there are that you're talking about, I guess. So looking at this, basically, everywhere the rectangular graph has a maximum or minimum, the polar graph will have an extrema, a relative maximum, a relative minimum, a relative extremum. So we can say this more mathematically rather than just say like, hey, look at the rectangular graph. We could say if r changes from increasing to decreasing, which means that r has a relative maximum, or decreasing to increasing, meaning r has a relative minimum, then r definitely has a relative extremum, and that will translate into the polar graph. So you can look at the rectangular, again, that's all I ever really do, is look at my rectangular graphs to determine what's happening on polar, but it's easy. If you can graph in rectangular, you can always turn it into a polar graph. So I think that's another kind of valid thing, like which of these values of theta will you have an extreme value on your polar graph? Just think about the rectangular and you'll know it. And then there's one more thing that, is true, so why not talk about it? The average rate of change for polar is like the outputs of polar, which are r values, divided by the inputs of polar, which are theta values. So average rate of change for polar, where the curve is called r equals f of theta, is going to be delta r over delta theta, which is f of theta 2 minus f of theta 1 over theta 2 minus theta 1. Average rate of change is always algebra 1 slope. But like, what does this mean? Well, it just kind of like approximates or gives you the average rate of change of r with respect to theta, right? So r is changing as theta changes. Like as you rotate counterclockwise, theta is changing. What's happening to r? Is r increasing? Is r decreasing? And then the kind of like units for this, I guess, you're talking about r is changing per radian. It's the rate at which r is changing per radian. So like r is changing by like 2 units per radian. So r will be increasing by 2 units every time the angle increases by 1 radian. That's what average rate of change with polar would be. That's it. We made it to the end of Unit 3. It's a pretty big unit. It's got a lot of stuff in it. It's basically the trig unit. I hope this was helpful, and good luck.